Pleasure to be here. Going to do a bit of a rapid fire on what non-destructive testing can help with bridge preservation. So looking forward to sharing some of our experience, some of the theory, some of the equipment, some of the applications. That's really what we want to share. Got some case studies at the end, and we'll save a little time for some questions. So as engineers, we really want to understand the cause. We had some discussions earlier about half-cell potential, corrosion. You sometimes can't see that. The techniques looking inside the concrete members, inside the bridge components, help us understand what's going on as far as deterioration. And when we can quantify that, that makes the condition assessment that much more effective and comprehensive. But we really want to try to go back in time. By the time the concrete cover spalls out and there's brown staining of the rebar, it's a little too late. We want to go back in time with ground penetrating radar, corrosion potential, looking at the potential for the deterioration and trying to catch it. That's where the preservation efforts are most effective. Now, I've surveyed, swung an S-wing hammer and done a lot. The white hatching, what you would hear, what our ears would tell us is delaminated. The yellow is some test methods that would show where that delamination has already occurred. But the red is where the corrosion is happening, and that's where there's going to be future deterioration and delamination. So deeper and deeper and looking inside is what's going to help us. We had some discussions on the Toonie Bridge about corrosion potential measurements, very valuable tool, ASTM 876. Once you make a connection to the real rebar, black steel, then all you need to do is just touch the surface of the concrete, and it gives you that potential difference, which is very valuable. Now, in 1974, Neil Young and Crazy Horse had an album, and the name of that is Rust Never Sleeps, and that's a true statement. So maybe that'll resonate with some of the classic rock folks here, and while they didn't name a song that, there was an album named of it. So we're going to get into energy wave propagation. Now, we record and analyze velocity information. We look at how energy waves get reflected and refracted off and through different material. We really want to record the velocity and then the amplitude. Some of this energy gets trapped in between the boundary conditions and it just oscillates. And by recording that frequency of that oscillation, we can get a lot of additional information. Bottom line, if it's faster velocity, it's probably going to be a stronger material. Now here is a picture, a blown up picture of an energy source, a ball projectile. I've got some other pictures of that. And we're recording two types of energy waves, a surface energy wave that travels along the face or the surface of the concrete, and then there's a vertical, there's an echo, a reflected energy wave that bounces off a boundary condition or an anomaly potentially, a void, a crack, a rebar. Now, a crack may soak up that energy like a dry sponge soaks up water, and we can get information on the depth of the cracks, and I'll go into that a little bit also. Now, I've got a schematic here that shows the one particular testing methodology, ASTM C597. That's pulse velocity. So that's more the surface wave, the velocity propagating out. Picture dropping a pebble in a pond of water, right? The ripples radiate out in 2 dimensions. And we record that velocity information with the sensors, the stethoscopes, whatever's touching the concrete. And we know the distance from the energy impact source, and we know the distance between channel 1, channel 2, 3, 4, and et cetera. And we can get a lot of information, velocity information, with this type of data collection. Another one that we record same data simultaneously is a vertical. It's a reflection or an impact echo test methodology. That's 1383. Again, both in the concrete spec. Now we're going to get the dimensions of the concrete. Let's say a concrete deck. That energy is going to go down to the bottom of the deck and it's going to oscillate between, let's say, 9.5 inches. And it gets trapped in there. So as we move along the deck, if there's delaminations in there, we'll have a 9.5-inch oscillating frequency and it might change to 3 inches. We know that there's a change and a conclusive evidence of delamination at that particular point. And then we can just move that over, record in a large different areas on where the concrete is, provide a visual observation of where the delamination is, and provide that as a result. Now here's a picture of it, the impact energy attenuator. It's one heck of a BB gun. It's got a photo eye on the end of it, fires a special steel bearing hooked up to a tank of compressed nitrogen. The same energy source, very repeatable every time we pull the trigger. We swing an S-wing hammer, that energy source is going to be a little different every time you swing it. And then we've got a 4-sensor array. It's about 30 inches. We know the distance from the energy source. Channel 1 and 2 are 6 inches apart, 2 and 3 are 12 inches, and 3 and 4 are 12 inches. So over that 30-inch lineal distance, we're going to get average velocity information and average thickness frequency information, and then we move it. And we set up data lines, survey grid lines, and collect information on everything. Now, the energy waves that we're looking to record, each one's a little bit different. Compressional wave is the first arrival, shear wave comes in later, and then the Rayleigh wave's got a little double hitch on it. And it's the first arrivals that give us the information. Once the second arrivals come in, there's energy waves bouncing all over the place. But the first arrival on channel 1, channel 2, channel 3, and channel 4, or whatever the sensors are, gives us the information, velocity information, and the frequency information. We've modified this equipment on a deck wheel, actually our 3rd generation deck wheel. That just goes along the deck, click, click, click. It has an automatic energy source, and the sensors are on the wheels, and those are spaced about 18 inches apart. Our experience has got the velocity information. We've developed a curve, and we can equate compressive strength to shear wave velocity and compressional wave velocity. And it's usually within about 500 psi after we collect a core. Sometimes there's some skeptics out there. I'll provide some information ahead of time on what the compressive strength values are. Cores break within about 500 psi. Let's remember that those cores are taken out of their element, shipped to a lab. When we're collecting data, we're getting what I might recall or refer to as in situ compressive strengths, and we're also getting it over a large area. One core, one data spot. We're going to shift gears, ground penetrating radar. It's still reflected energy, but it's electromagnetic energy. The transmitter and the receiver are all in the same shielded unit, but there's different frequency antenna. The high frequency range, we're picking up rebar in concrete. Low frequency range, call before you dig, looking for utilities underground. But we're looking at the electrical density of the material based on how the electromagnetic energy is reflected back to our receivers. Whatever's conductive, salt is very conductive, salt water, brackish water, there can be residue in the soils. Sometimes that doesn't work very well. And different antenna frequency are going to give you different information on penetration and resolution. 200 megahertz frequency, good for locating bedrock, about the deepest penetration. 400 megahertz in the middle, sinkholes or approach spans. 900 megahertz, bridge overlays. What's the asphalt thickness? What's the deck thickness? How much soil might there be on an arch? Very important for some of the load rating requirements. A mini or a high frequency is more designed to identify rebar in concrete and pick up air voids and different ones. Self-contained unit, very, very effective. Each one of these little parabolas is an individual rebar, so we've got depth on the left and station distance across the top. Where it's washed out on the right, there's some moisture, some air voids, something's getting in there that after station 78, it's distinctively different than prior to that, but this about 6-inch spacing with about 2.5-inch cover depth. Or a different frequency antenna is going to say that we got 4 to 6 inches of an overlay, then there's a deck slab, and then there's a void under the deck slab. The high frequency is not going to get this information, and sometimes even multiple antenna frequencies are going to pull this all together. Seismic refraction, a bigger bang and a longer list of sensors. So we're talking 100, 200, 400-foot long lines of hydrophones or geophones laid on the soil or in the river, and an energy source is a black powder or a sledgehammer on the bedrock. The ratio, the 3 to 1, you need about 3 times the surface distance for the vertical. You want to go down 100 feet of information, we better have 300 feet of sensors on the surface. And rock strength is defined as a shear wave velocity to this day. Caterpillar uses it to define rock strength, as does RQD and compression brakes. So there's the black powder energy source on the left and a rock outcropping on the right. We hit it, we listen, we determine the relative depth to the bedrock and can get profiles on all of that. So a little theory, now we're going to get into some applications, conscious of my time here. Honeycombing, QA/QC, take the forms down. Now we've got consolidation issues or a horizontal cold joint, right, is waiting for a truck in the summertime as the top part of the concrete bonded to the bottom. Well, if the energy crosses that cold joint, the answer is yes. If the energy doesn't cross that cold joint, the answer is no. And sometimes some of the concrete needs to be removed. So a good 1-2 punch is the impact energy, or excuse me, the impact echo, pulse velocity, and GPR for assessing walls or abutments or piers. And those are all surface testing, right? The energy is on the surface, the sensors are on the surface. If we have access to both sides of a concrete member, then we can do some through testing, very similar to what the medical community does with CAT scans. They create an image of our heart or our brain or our spleen, and then they slice it into different slices, tomographic images. A lot more data to collect, a lot more data to analyze, but we can get detailed information of the internal structure of the concrete. If there's a crack, by separating the energy source, walking it away from the crack, or walking the sensors or the energy source away, we can get the relative depth of the crack. Often we'll look at shallow depth cracks, say 0 to 3 inches, medium depth cracks 3 to 6, or greater than 6. We can't really pinpoint it, but by looking at the crack, you have no idea of how deep it is. This information provides some additional value. Testing piles. Now we're using the echo, the reflection part of those energy waves. And as they propagate down to the bottom, they will get reflected off the tip of the pile and come back. If there's an inclusion in, say, a drilled shaft or a concrete pile, maybe groundwater, we pulled the cans too early and they're creeping in there, we may get a secondary reflection at a shallower depth. So we measure the velocity of an individual pile, we record the two-way travel time, calculate the length. We do that with timber, steel, and concrete piles. A couple of examples of pile length testing. We need access to the top or the side. Sometimes that requires some excavation, sometimes it requires a boat. The timber piles, we put the sensors with a ratchet strap around there. There's another one just out of that image to get the velocity, and sometimes a hammer works. Sheet pile, concrete-filled pipe piles, all types of piles for pile length. And the other application is grouted tendons, where there may be voids. Now, if it's a solid grouted tendon, like on the left, that energy is going to go right through it. If there's an air void, it's going to go around it. It's going to stay in the concrete. And by looking at the velocity and the frequency of the reflected energy, we can get the thickness information, and we can determine where there are grout voids. Some external post-tension tendons inside a box girder, internal post-tension tendons for the box girder or some of the substructure units. We can find the voids, and I've got some examples of those. So, case studies. We're going to save some time for some questions. Consolidation issues. So there was precast members coming up out of the water on this large pier, and then there was another precast member going up to the superstructure, but a closure pour in between. So I'm concerned that there was some consolidation issues within that closure pour. The blue is just, we can set up the schematic to match the velocity or ultimately match the compressive strength. Blue is 7,000 PSI. Green, 3 ticks over and 4 ticks down, is not 7,000 PSI. But it's not red, it's not a coffee cup, it's not a void, it's just not 7,000 PSI. We had a lot of the information, had access to both sides of the closure pour, did the slicing, provided this information to the engineer. They work with the owners, what's the assessment, what's the response, pretty isolated situation, and this was determined to be negligible. No plans. Everybody got plans for all their bridges? Probably not. So this abutment had no plans information, didn't know how thick it was, didn't know the geometry, didn't know what the bearing capacity or what it was sitting on. So ground penetrating radar horizontally is going to give us that information. There was a masonry facade, had that beautiful graffiti on it. That shows up as the yellow or on the left image. And then the general shape of a battered gravity abutment is what we would expect. A little disturbance zone where the excavation took place shows up as well. And then we oriented it vertically. Bedrock was about 4 feet down. So with no information before, was able to quantify a lot of information on this particular abutment and what it was founded on. Seismic refraction, proposed alignment for a new bridge over a river. And we, in 2 days, was able to map out bedrock profiles over 1,400 lineal feet, continuous profiles. And they were still Owners and engineers were still focusing on the span lengths and whether it was going to be shallow or deep foundation. Our information gave rock strengths and rock depths. Shallow foundation was applicable. It was only down about 12 to 16 feet and very valuable early on in the design process. I'll also mention that the seismic refraction is valuable prior to a subsurface investigation program. It's not going to tell you the bearing capacity, but it might reduce the number of borings and tell you where to strategically locate them. A big advantage if you have a project like that. Deck wheel and GPR, that's the 1-2 punch. Let's look at a deck. We can cover a typical, 2 main spans, 2 approach spans in about a day. We need some traffic control, alternating traffic at the left side in the morning, right side in the afternoon. Green is relatively good concrete. Orange or red is where some of the delaminations or the weaker concrete is. They're at the expansion joints, they're at the scuppers, they're where the puddles are. Very typical of what you would expect. Interesting local bridge here, there was perforations in the water line of these H-piles picked up in the bridge inspection. And there was going to be a posting on that, and they needed to repair that. So before they dug into the riverbed, they said, well, we ought to find out how deep the piles are and see what type of piles are. So we came out within one day. We did a refraction assessment, determined the bedrock depth was about 22 feet from the water surface. We tested the length of the piles. You guessed it, 22 feet from the water surface. So we knew they were end-bearing piles and safe to dig down into the riverbed, put some splices, repair the metal perforations. Bridge was not needed to be posted, and the flag was removed. Here's an interesting one. Box beams. We're supposed to have 5.5 inches, right, of cover around. That is what the pre-stressing strands and the rebar and stirrups are all embedded in. Didn't have 5.5 inches on the bottom. Now this is oriented from the bottom. We're looking up. The green line is the bottom of the beam, and that's at 5.5 inches. So the total thickness up at the top where the scale is 5.5 inches. The red line is the concrete that was there, and there were big voids. It was not flush up to the styrofoam cutout. And you're thinking, well, isn't that the pre-stressing and the rebar exposed then? And the answer is yes, and they were corroded, and that is not good. By the way, the rebar or the pre-stress manufacturer that made these beams are no longer in service or no longer in operation. Precast, you'd think with a precast structure you'd have plans. Not always the case. We'll find out the rebar spacing, find out the concrete strength, the thickness, the geometry. That's needed in the load rating that goes with a bridge inspection. Scour is important. Concern, everybody remembers back in the 90s and 2000s the requirements to look at the existing structures, the 113. You couldn't rate them U or 6. Those were the unknown foundations. So a lot of the testing that we do helped quantify the reinforcement details, looked at the dimensions, how deep are the piles, if there's a stability analysis to be done based on theoretical scour depths. Embedment depths in the river, need to know that. That's critical in assessing that. Seismic refraction, now I'm from Niagara Falls, and yes, rock erodes, but if the abutment's founded on rock, we can use that with the vulnerability assessment and assign a 113 rating. Or if riprap has been covered over, maybe there's been some sediment that has gone by and covered over the riverbed, and you might have nice big riprap 24-inch down below, but there's 6 inches of sediment. Depending on the water conditions, we can quantify that there is riprap there. Post-tension tendons, grout voiding. So we got to find the tendon ducts. GPR will find it. We can differentiate between rebar, which is on top, those parabolas, and the tendon ducts, which are below that. And sometimes they're stacked up like bowling pins, and that does present some challenges for us to get the grout voiding. But once we know where the tendon ducts are, we've snapped a line, we can go with the impact echo pulse velocity testing directly over the tendon duct and find out where we think the voids are, where there's not grout, or grout that just never set up, or water. Now we do have to do some openings. Each bridge, each grout, each tendon duct's a little bit different, so we find where we think there's a void and we carefully drill in and open up the tendon duct, and with a bore scope can quantify what conditions are inside. And the real question is, are the strands corroding? And where are the voids? And here's a mishmash of conditions that are not fully grouted. Top row, third one over, that's a Dewey dag bar. We didn't even have any strand wire in that one. Bottom row all the way over, that's a vertical shot. That's water that's reflecting back. Some of these voids are 10, 15, 20 feet long. And once we quantify a couple of the openings where the voids are, we don't have to open up every one. But once we ground truth it, validate our data with a couple openings, we can portray that all the way forward. Really interesting project here. We're trying to salvage and preserve the substructures. The deck was coming off, superstructure was shot, but the piers had scour protection. They were on piles, but how good's the concrete? The outside of the concrete looked pretty bad. Rebars visible, spalled off. There was a shotcrete repair that had failed. It did take some cores, photography, chlorides. There's value in that. But we were able to do through testing of the pier. And the outside of this pier, in the top right red image, was the surface testing results, 0 to say 6, 7, 8 inches deep. Very weak concrete, less than 1,000 PSI. But the blue is a representation of the core compressive strength of that pier. That's over 5,000 PSI. This can be chipped away, drill some dowels in there, overpour it, and salvage the pier, and that's exactly what happened. We also did some corrosion potential testing here, and that was fine. Just wrapping things up, we've mounted our impact echo pulse velocity testing on an underwater ROV. I don't think anybody's done that. We can get compressive strengths of concrete underwater from an ROV. Some places you just don't put divers. Our equipment for pile testing is also waterproof, and we put it in the hands of divers all the time because sometimes the only access to the pile might be below a jacket or below the water. But here's an example, ASI Marine. Talk to me if you've got any interest for that. Not really a bridge, but a pretty unique application. And the last slide here is for the Federal Railroad Administration. About 10 years ago, we had a grant to test for cracking in concrete rail ties. Well, we couldn't use contact sensors, so we got into microphone technology and proved to ourselves that not only can we feel the shear wave, compressional wave, and Raleigh wave, if we know what to listen for, and we amplify that, we can hear those waves and pinpoint when they go by our sensors as well. We were just awarded another grant for that started this month, and we need this to go faster. This version was a walk behind. Everybody wants it to go faster. Talk to me in 6 months, and I'll let you know how we make out.